Hey there, Mr. Sutton here with the BC Calculus 712 Part 2 homework solutions on limit comparison test. On this problem, we're trying to figure out the convergence of this series here. So this one looks pretty close to the harmonic, so we're going to try comparing it to that because none of the other tests really work all that well. So compare it to 1 over n, and again, that's the harmonic series which we know diverges. Now, which comparison test to use on this one? Well, the numerator is bigger, but the denominator is also bigger. That's going to give us kind of mixed results if we try to compare this thing as to whether it's greater or smaller than the harmonic. So we're going to be on the safe side and use limit comparison for this one. Let's start by verifying these are both positive series. So we've got this first series here being positive for all n values 1 or greater. Second, same thing for the harmonic series. So since these are both positive for n greater than or equal to 1, we can go ahead and use limit comparison. So let me take the limit as n approaches infinity of the original series over the comparison series, the harmonic series in this case. Same change flip, that's going to give us 5n over n plus 1. And as n goes to infinity, this little plus 1 just goes away. We've just got 5n over n, which is 5. Now, since that limit, which I'll call L, is between 0 and infinity, since this limit is a finite number that's positive, and since our comparison series diverged, that means our original series is going to diverge by the limit comparison test. On this problem, we're trying to find convergence or divergence for this series. So this one doesn't really work great for nth term test or really a whole lot of other things. But we could try a comparison test on this one. So we've got, in general, I'm going to compare this to n over n cubed. That's a pretty close series. And n over n cubed, that's really 1 over n squared, which is a p-series with a p-value of 2. Since that's greater than 1, that means our comparison series here is going to converge by the p-series test. So if we compare this to the original, it looks like our comparison series is actually going to be smaller than the original. The original has a larger numerator and a smaller denominator. So this is kind of the wrong direction if you want to use direct comparison. So we'll use limit comparison instead. Our original is a positive series, and the comparison series, 1 over n squared, is also positive, and that's true for n values greater than or equal to, let's say, 2, because this denominator here, if you plug in 1, that's going to come out negative, so we'll start at 2. So now using limit comparison, we have limit as n approaches infinity of the original over the comparison series, 1 over n squared, and I'll let whatever this comes out to equal L. So now same change flip, we've got n squared times 3n plus 2 in the numerator, and n cubed minus 2n in the denominator. If we distribute this, this is going to be 3n cubed, and I don't really care about the rest because my limit's going to infinity here. So we have 3n cubed over n cubed, ignoring those lesser terms as n goes to infinity. We just end up with 3 for this limit. Since this is a finite positive number, since my L here is between 0 and infinity, and since my comparison series converged, that means my original is going to converge by the limit comparison test. For this problem, we want to figure out if this series converges absolutely, conditionally, or not at all. So we start by considering the absolute case of this series. So I'm just going to consider this without the negative 1 to the n, so just 1 over all this jazz. And for this one, this is going to be one that, it passes the nth term test. The ratio test doesn't really work out so well. It's kind of a p-series and kind of not. So I'm going to compare it to a p-series. Let's compare this to 1 over the square root of n, because I bet it behaves pretty similarly to this function here. Now, 1 over radical n, that's really just a p-series with a p-value of 1/2. Since that's less than or equal to 1, this comparison series diverges. And now it looks like here this original is going to be actually less than the comparison series. So that's the wrong direction for showing divergence. We'd like our comparison series to be less than the original if we're trying to show divergence. So we're going to use limit comparison rather than direct comparison. So let me verify these are both positive series. This first one is definitely positive for any n value greater than or equal to 1. Same thing with my comparison series. So both positive for n greater than or equal to 1. So I can use limit comparison. Let me set up a limit then. I'm going to let L equal the limit as n approaches infinity of my original over my comparison series, so over 1 over radical n. Same change flipping this thing. I've got radical n over root n plus 1. And for this one now, as n goes to infinity, we can ignore this little plus 1. So this is really n over 2 root n. Root n's, or it's root n over 2 root n, so root n's cancel out. This is just 1/2. Since this is a finite positive number, in other words, a number between 0 and infinity, and since we diverged for the comparison series, that means the original is, or at least this absolute version value of the original is going to diverge by the limit comparison test. So that doesn't mean we're done with the problem. It just means we don't converge absolutely. We still have to check for conditional convergence, though. In other words, do we converge if we allow the alternating part of the series to happen? So if we allow for this -1 to the n, if we just look at the original, we see that we do have an alternating series that is decreasing in absolute value to 0 since my denominator is growing. Since we have these conditions, that means that the original is going to converge conditionally by the alternating series test. On this problem, I want the interval of convergence for this series. So let me start by seeing if this is geometric. It's not. So I'm going to go ahead and use the ratio test instead to find the interval of convergence here. So I've got the limit as n approaches infinity of absolute value, so we can forget about this -1, of we've got the n plus 1th term over the nth term. So the n plus 1th term, that's going to be x to the n plus 1 minus 1, so just x to the n over n plus 2. And now the nth term, that's going to be x to the n minus 1 over n plus 1. Again, we can lose the -1 because we're doing absolute value here. Same change flip. We've got x to the n times n plus 1 in the numerator. And we've got n plus 2 and an x to the n minus 1 in the denominator. These x's can cancel out a little bit. Subtracting my exponents, that's going to leave me with, let's see, just an x upstairs. So x and an n plus 1. We still have this n plus 2 downstairs. As n approaches infinity, I can disregard this little plus 1 and this plus 2 next to the n's. So n over n is just going to cancel in that situation, leaving us with just an x inside the absolute value. And to find the interval of convergence, we'll let that be less than 1. Rewriting this without absolute value, we can write -1 less than x less than 1, question mark, because I don't really know if I'm converging or not at these endpoints. With ratio test, I always have to test those endpoints. So if x equals -1, what does that do to the original series? Well, we're going to have -1 to the n minus 1 times -1 to the n minus 1. Since we have the same exact exponent, we can multiply the bases together to get just +1 to the n minus 1. So when the dust settles, this is really just 1 over n plus 1. So this is pretty close to the harmonic series. In fact, if you actually just start writing out the series, you've got 1 over 2 plus 1 over 3 plus 1 over 4. So this is actually just the harmonic series starting a little bit later down the line. Now, if you didn't recognize that, you could use a comparison test. We can compare this to the harmonic series, which, since it's the harmonic, we know it diverges. And for this one, if you're trying to use direct comparison, that's going to be a little bit tricky because the original is less than the harmonic series because we have a larger denominator. So that's the wrong direction for direct comparison, but we could still use limit comparison. So to do that, we have to verify that the original is greater than 0 and the harmonic is greater than 0. And this is going to be true for n greater than or equal to 1. So now, limit comparison, we have L equaling the limit as n approaches infinity of the original over the comparison, so 1 over n down there. Same change flip, we've got n over n plus 1. As n goes to infinity, this comes out to a limit of just 1. Since that's a finite positive number, since L is between 0 and infinity, and since the comparison series diverged, that means the original is going to diverge by the limit comparison test. So long story short, we are diverging at this first endpoint. Now how about at x equals positive 1? Plugging that into the series, that's going to basically just get rid of this x to the n minus 1, because 1 to whatever is just 1. So we just end up with negative 1 to the n minus 1 over n plus 1. Now this is a series that is alternating, and since our denominator is growing, we're also decreasing in absolute value to 0. These are the conditions for saying that this converges by the alternating series test. So since we're diverging on the first endpoint and converging on the second one, we can write for our final interval of convergence, negative 1 less than x, less than or equal to 1. On this problem, we want to know which of these series converges, so we'll have to go through them one at a time here. So for series 1, if you just look at what's happening here, we're adding 1, subtracting it, adding it, subtracting it over and over again. So this is oscillating between 1 and 0, which means it's never going to converge. It's going to diverge by oscillation because it doesn't come out to a single finite value. So we can eliminate 1, so anything with the answer choice 1 in it is gone, such as choices A and E. So now it's down to 2 and 3. So for the second one here, just looking at our general term here, this looks vaguely harmonic, but there isn't really anything we can do to quickly get to the root of this without using a comparison test. So I'm going to compare this to the series 1 over n, which is the harmonic series, which we know diverges. Now this series here is going to be, let's see here, it's hard to tell whether this is greater than or less than the harmonic series. Eventually, this is going to be less than the harmonic series because as n gets bigger and bigger, you get a denominator that's progressively smaller and smaller compared to the original here. That's the wrong direction for direct comparison, so we'll use limit comparison instead. So I'm going to say that my original is greater than 0. 1 over 2n minus 1 is greater than 0, as is 1 over n. But I have to be careful about the n value that I say this for. So we'll say an n value of 1 or greater. That'll work. So now let me take the limit as n approaches infinity of the original over the comparison series, 1 over n down there, and I'll let that equal L, whatever that comes out to. Same change flip, we've got n over 2n minus 1. As n goes to infinity, we can forget about this negative 1, so it's just n over 2n, which is 1/2. Since that is a positive finite number, a number, in other words, between 0 and infinity, and since this comparison diverged, that means the original is going to diverge by the limit comparison test. So that eliminates answer choice, or option 2. So anything with a 2 in it is gone. Well, that eliminates the other remaining answer choices, B and D, so it must be C, even without having to prove that this converges, but we can prove it converges pretty quickly. This is pretty close to a P series. Actually, no, this is a geometric series. A geometric series, we have a common ratio. We're multiplying each time by 1/3. So absolute value of our common ratio is 1/3. Since that's less than 1, this converges by the geometric series test. So yeah, we can choose answer choice C. On this problem, I'm trying to figure out which of these 3 series converges, and it could be more than one of them, but not all 3 if you look at the answer choices here. So let's start with this first one. Now this one, sine of n, absolute value, that's going to be no bigger than 1. So I'm going to compare this to 1 over n squared, just to get to the bottom of this one. And that's going to be, let's see, that's a P series with a p-value of 2. Since that's greater than 1, the comparison series converges by the P series test. Now comparing it back to the original is always going to be less than or equal to 1 over n squared, because again, absolute value of sine, the biggest that's ever going to get is 1. It's usually going to be less than 1. So I can write 0 less than or equal to the original, less than or equal to 1 over n squared. And that's going to be true at n values of 1 and greater. It's immediately true here. So because I have a series that is smaller than something I just showed converges, that means my original must also converge by direct comparison. All right, so anything with option choice 1 is still good. Anything without it is not good anymore. So we can eliminate B and C. So really it's down to D and E. 2 and 3 can't both converge just the way these answer choices are set up. It's one or the other. between the two of these, I'd say 2 is probably going to be the easier one to figure out, but we'll test both of them just for the sake of showing how to test these. So this next one, this is really 1 over e to the n, which is a geometric series. So we've got 1 over e as our common ratio, the absolute value of our common ratio, in fact. Since that is less than 1, e is bigger than 1, so dividing by it's going to give you a number less than 1, that means that we're going to converge by the geometric series test. So that means if you wanted to, you could stop right here, pick answer choice D, and be on your way, because 2 and 3 can't both be true on this one. But let's go ahead and just look at 3 if you want, just for the sake of figuring out how would you prove convergence for this. So this is pretty close to the series n over n squared, so I'll compare it to that series. That series reduces to 1 over n, which is the harmonic series, which we know diverges. So now we have to pick a comparison test. Well, between the two tests, it's kind of hard to tell whether this original series is going to be smaller or larger than the harmonic. Our numerator is bigger, but so is our denominator, so that's kind of ambiguous. In cases like this, we check out limit comparison. So first off, I have to show these are both positive series. This original series definitely positive for n greater than or equal to 1. Same thing with the harmonic. So for n greater than or equal to 1, both greater than 0. So now let me take the limit as n approaches infinity of the original over the comparison series. And I factored the original a little bit here, just for kicks and giggles, I guess. But now here's our n value down here for the harmonic series. Same change flipping this thing. We've got n times n plus 2 in the numerator and n times n plus 1 in the denominator. Well, these two n's cancel out immediately. That's probably why I factored it. But now, as n approaches infinity, this plus 2 and this plus 1, we don't really care about those either, so we just have another n over n that's going to cancel, leaving us with a total limit of 1. That's a finite positive number. It's a number between 0 and infinity. Since that's the case, and since the comparison series diverged, that means the original here, option 3, diverges by limit comparison. So this confirms what we said earlier, that only options 1 and 2 are going to converge, so answer choice D. For this problem, we're trying to figure out all p-values for which this series diverges. Now, looking at the answer choices here, it looks like everything revolves around 1/2. So what's happening when p equals exactly 1/2 here? That's a good question to ask. If p is 1/2, 2 times 1/2 is just 1. So this would be n plus n, or 2n. That's vaguely harmonic, which would make the series diverge. You could eventually show this with a limit comparison test, or just factoring out 1/2 from the series and having 1 over n inside here. Now, if p is less than 1/2, well, that's going to make this diverge even more than the harmonic. So p is definitely going to diverge for p less than or equal to 1/2. But we also have this option for p diverges for all p. So how about if p is greater than 1/2? Well, in that case, you're going to have something with a higher exponent than the harmonic series, which we can eventually show with limit comparison, and p series is going to converge. So you could pretty quickly pick answer choice A, just thinking about what happens with this exponent here. If you have to rigorously prove it, it's going to take a little more time. So multiple choice, you can quickly pick A, but I'm going to go ahead and prove what I just said using some comparison tests. So there's two cases here. Let's consider the case where p is less than or equal to 1/2. So in that case, let me start by establishing my comparison series. I'm going to compare all of the possibilities here with p less than or equal to 1/2 to the series 1 over n, the harmonic series, which, as we've said before, diverges. So just to verify a few things, if I'm trying to prove this with direct comparison, it's going to be a little tough because adding this n here, I've actually got a larger denominator, so a smaller overall result in the original. If you're smaller than something that diverges, that's inconclusive. So I'm going to have to use limit comparison instead. I can verify that the original is greater than 0 for all n values greater than or equal to 1. Same thing for the harmonic. So for n greater than or equal to 1, these are all positive. So now using limit comparison, I can say L is going to be the limit as n approaches infinity of the original over the harmonic series. Same change flip, we've got n over n to the 2p plus n. And this is where we have to pay attention to what p is in this case. Because this whole n approaches infinity thing, it's going to depend on what these exponents are, who gets eliminated. Now, if p is a number less than 1/2, that means the exponent on this first n here is going to be less than 1, which means this is going to be a slower growing term than the n over here. So as n approaches infinity, in this case, we can rewrite this limit as n over n, which is just 1. Since that is a finite number between 0 and infinity, finite positive number, and since our original diverges, that means all series where p is less than or equal to 1/2 in this situation are also going to diverge by limit comparison. So that's the first half of what we had to show. We've shown that at the very least this series diverges for p less than or equal to 1/2. So we can eliminate b because it doesn't have the equals. We can eliminate c because it doesn't have diverging for less than 1/2. And certainly d is also flawed. So really it's down to choice A or choice E at this point. So now we have to figure out convergence or divergence when p is greater than 1/2. So we'll do that on the next slide here. So now we're just considering cases with p-values of higher than 1/2. So in this situation, I'm going to compare this to 1 over n to the 2p. In this case, 1 over n to the 2p, this is a p series with a p-value, and I'll put p in quotation marks, a p-value of 2p. So this is going to converge if p is greater than 1/2. So this is going to converge by the p-series test, because if p is greater than 1/2, that makes this greater than 1. So this converges. I'm going to use limit comparison on this one. So this is a positive series, and this original is also positive. So the original is positive. My comparison series is positive for n greater than or equal to 1. Using limit comparison, I've got the original divided by the comparison. Same change flip, we've got n to the 2p over n to the 2p plus n. Now, if p is greater than 1/2, that's going to make n to the 2p the dominant term in the denominator. So I can write this as n to the 2p over itself, which is just 1. This is a positive finite number. Since this is a value between 0 and infinity, I can say that, and since the original here, or the comparison here converged, I can say this original is also going to converge by limit comparison. So it doesn't diverge. We only diverge if p is less than or equal to 1/2. We've rigorously shown that, so that's going to be answer choice A. On this problem, we have the Maclaurin series for some function given by this stuff here. And our first task is to use the ratio test to find the interval of convergence. Well, this was nice of us. They told us to use the ratio test. So let's go ahead and do that. So we need the limit as n approaches infinity of absolute value of n plus 1th version of this. So that's x to the n plus 1 over n plus 3 over the nth term, which is just x to the n over n plus 2. Same change flipping this thing. We've got x to the n plus 1 times n plus 2 in the numerator. Denominator, we've got n plus 3 and x to the n. These x's can cancel out a little bit, leaving us with just an x and an n plus 2 in the numerator, just n plus 3 in the denominator. As n goes to infinity, the little plus 2 and plus 3 can be ignored. So that's just n over n, which cancels out, leaving us with x inside absolute value. And we're going to set that less than 1 as part of our ratio test. So our interval of convergence then, writing this without absolute value, is kind of our rough draft of this is going to be -1 less than x less than 1. I put a question mark here because we still have to test those endpoints for convergence. So at x equals -1, what does that do to the original series? Well, we're going to have -1 to the n over n plus 2. This is an alternating series, and since my denominator is growing, we're decreasing in absolute value to 0 for all the terms. So that means we're going to converge by the alternating series test. Now how about if x equals positive 1, my other endpoint? Well, in that case, I've just got 1 over n plus 2. So you could save a little bit of time. If you start writing this series out, you'll see this is 1/3 plus 1/4 plus 1/5, which is basically the harmonic series starting a little bit later down the line. Or if you didn't realize this, you could compare this to the harmonic series, 1 over n. The harmonic series we know diverges. Now, if you're trying to prove divergence by comparison, this is the wrong direction for things to be in. The original has a larger denominator, so smaller overall value than the harmonic. It's hard to show that something that's smaller than a diverging series also diverges. The other way would be easier. So we're going to use limit comparison instead of direct comparison for this. So let me establish that these series are both positive, and they are. 1 over n plus 2 is greater than 0, as is 1 over n, for n values 1 or greater. So now let me take the limit as n approaches infinity of my original, 1 over n plus 2, over my harmonic series, my comparison series. Same change flip, that's n over n plus 2. And I'll let this equal L. This limit is just going to be 1. Since that's a finite positive number, in other words, a number between 0 and infinity, and since my comparison series diverges, that means this original series also diverges by limit comparison, which is enough to show that our final interval of convergence needs to be -1 less than or equal to x, less than 1. For this part of the problem, they're saying g is f of -2x. We want the first three terms in general term of a Maclaurin series for g. Well, we've got the Maclaurin series for f. To get g, we just have to substitute -2 for all the x's up here. So going from left to right, first three terms, we've got -2x over 3. Next, this is going to be, let's see, -2x squared. That's going to be 4x squared over 4, which is just positive x squared. Next, we're going to have -2 quantity cubed over 5. So that would be, let's see here, -8x cubed over 5. And now for the general term, we're raising to the nth power this -2 and an x. So I'm going to separate things out. We're going to have a -1 to the n, we're going to have a 2 to the n, and we're going to have an x to the n all over n plus 2. So there is our general term, and that's all they actually wanted us to do. For this problem, they're telling us the first two terms of this series are used to approximate f of 0.1. They're giving us the absolute value of our third derivative is less than or equal to 0 on the interval 0 to 0.1. They want us to use Lagrange to show our approximation differs from the true value by at most 1/3000th. All right, well, setting up our Lagrange form here, we've got error less than or equal to big fraction. Up top, we have the max derivative, the max next derivative. Now, since we use the first two terms, and that's, let's see, quadratic base, this is a quadratic approximation, basically. That means that everything in our Lagrange form is going to have to be third, pretty much everything. So third derivative, third factorial, third power. So we have the max third derivative on the interval from 0 to 0.1, because that's what they gave us. And also, it's Maclaurin series, so we have to go from the center to the approximation x value. Now we wanted max third derivative in absolute value. We've got third factorial, and we have x minus a, which in this case is just going to be 0.1, or 1/10 to the third power. Okay, so let's go ahead and simplify this a bit. The max derivative, they already gave us that right here. They said the derivative is always less than or equal to 2 on this whole interval. So we'll write 2 up here, still have a 3 factorial and a 1 over 10 to the third. Let's simplify this a little bit to show that this is clearly less than or equal to 1/3000th. So this is really, let's see, 2 over 3 factorial, that's really 2 over 6, or 1/3. Over here we have 1 over 1,000. 1/3 times 1,000th is 1/3000th exactly. So that just meets the cutoff for what they gave us, and we are done with the problem.